Welcome back to the EasySpin Academy 2020, which happens entirely online this year. This is day 2 of our 3-day workshop, and today we're going to cover mostly least squares fitting, plus some more details about EPR spectral simulations. Before we start, I'd like to review the basic logistics of this course for those who join us today for the first time. If you go to the EasySpin website, there's a link to the EasySpin Academy website. So easyspin.org, and then click the red link and it will take you to the EasySpin Academy website. And all resources are collected there. There's a schedule, and to remind you about the schedule, we're going to proceed with 6 30-minute sessions with a 10-minute break in between each of them. And the sessions consist of demonstrations for the first about 20 minutes, and then you have about 10 minutes to explore exercises and documentation. The live stream is on YouTube, as you are watching to right now. Ask questions on the EasySpin Slido website, and that looks like this if I fire it up, and people will try to answer as quickly as they can there. In between sessions, I will also chime in, and if you are an EasySpin expert, please also help out answering questions of the beginners that are posted on Slido. The demos and exercises are downloadable as a zip file, so everything I do and write today is already pre-delivered to you in forms of MATLAB scripts. So you don't have to worry about taking extensive notes or following along with the typing I'm doing. Some of my typing is pretty fast. Sometimes I do copy-paste. So don't worry, all these scripts are available already, and solution to the exercises will be posted after the end of the workshop. Importantly, at the end of today, at noon Seattle time, which is I think 9 p.m. Central European time, we'll have a virtual happy hour again like yesterday, and it's on gather.town. The link is also on the main website. I encourage you to attend because a lot of the EasySpin folks are there, and this is a great opportunity to ask individual questions. And I will be there for the full 2 hours that the happy hour is running. So catch me there and we can discuss any of your needs for EasySpin. The workshop is based on the latest version of EasySpin, the development version 6.0.0-dev.26. Some of the features I'm showing are not available in the previous versions, 5.2.28. So if you want to reproduce what's happening in this workshop, I recommend using the development version. The development version is already fairly stable. It's just not yet feature complete. That's why we don't have a 6.0 final release yet, but we're working towards that. And finally, the last link shows a t-shirt campaign on bonfire.com. You can purchase our EasySpin Academy 2020 t-shirts. Any of the proceeds go to a foundation, so we don't make any money from that. Okay, with this, let's go back to MATLAB. So EasySpin is based on MATLAB, and it contains mostly scripts and functions. So in order to use EasySpin, as we saw yesterday, you have to write out a little bit of code. If you're not into coding and this is your first encounter with code, it might be a little bit of an entry barrier. But once you get into it, you will see that it's actually much more reusable. You can just save a script and reuse it months later without having to retrace your memory to figure out, oh, what did I click there? Oh, and how did it work? It's all in the script. Scripts make your research and your analysis much more shareable and reproducible. That is one reason we use scripts in EasySpin. And the other reason actually is that EPR spectroscopy is such a wide field with so many different applications that it's really hard to wrap everything into a single graphical user interface. So today we're talking about least squares fitting. That is one of the few places where EasySpin does have a graphical user interface. And the function that fires up that interface and does the least squares fitting is called esfit, where the ES stands for EasySpin. And it's a wrapper around a lot of different fitting algorithms, and it's dedicatedly constructed to work with EasySpin spectral simulation functions. So let's get started. Let's start with the simplest possible approach. Let's load some data. As yesterday, I have open here the editor pane on the left, and on the right bottom I have the command window, and then right top I have the workspace where I'll see the list of variables, and I will also dock any figures that will appear into this top right workspace. Okay, let's load some data. And for this we use the function EPRLoad. And we're gonna load a mock iron sulfur cluster spectrum. So we're telling EPRLoad the file name, and DTA, as many of you probably know, it's the Bruker EPR file format, but many other formats are supported as well by EPRLoad. For example, SpecMan, Active Spectrum, Magnetec, Adani, and JOL, and so on. So in return, we'll get the magnetic field vector and the spectrum. So I can run this code. I could copy paste it over to the command window by just selecting this, Control-C for copying, and then over here Control-V for running it. However, it's much easier to just press Control-Enter on Windows or Command-Enter on Mac to get this running. Okay, well, let's add one more. Let's do the plotting as well, and now press Control-Enter. And voila, we've got a figure that shows a mock iron sulfur cluster spectrum. I'm docking the figure here, moving it over with click and hold to the designated place in my preferred layout. Okay, in order to least squares fit, to invoke least squares fitting, we have to define the experiment that actually gave these data. And so we say exp.microwave MW equals, I think it was 9.5 for this spectrum. And we also have to define the field range. Now the field range is of course given by the data, right? And it looks like it goes from 300 to 380. So I could type in those two numbers directly, right? 300 and 380, and it would be fine. However, let's add the node millitesla here. However, if I then change the file here, I might run into an error if I forget to change the field range for a different spectrum. So a much more reusable way of doing it is just take the B vector and then pick out its minimum value. And that is done by typing min of B. This will just look through all the elements of the B vector and pick out the smallest value, which is the starting field of the scan. And then the end field of the range should be the maximum of the B vector. If you write it this way, your simulation range will always match the experimental range, even if you change the file name. This makes your code less error prone. We also need to specify the number of points. Different spectrometers might use different number of points depending on acquisition conditions. So in order to do that, we use the field exp.endpoints. And now again, I don't want to just look how many points we have. I want to make this a little more reusable. Well, let's first go look. Click on workspace, and you can see there's two variables here. One is the magnetic field and one is the spectrum, and both of them are vectors with 1024 elements times 1. So endpoints would be 1024. But again, a more usable way of doing it is just to tell MATLAB to use the number of elements, num_L, in B. In case you change your spectrum again, this will make your code more robust. So now we've set up the experiment. Now let's set up the spin system with some starting parameters to do the fitting. Let's click the spectrum back here. So let's say let's call it sys0, 0 indicating these are just our starting values. And we could have done some analysis here. And maybe we read off something like this. 1.9, 2.0, and 2.08. And we'll also add some broadening. And now if you look here in these data, you can see that the low field feature is sharp, the high field feature is broader. And this indicates that we have some anisotropic broadening going on. And in order to model this anisotropic broadening, you have to ask yourself, what is the broadening mechanism? Is it unresolved hyperfine couplings? Or is it a result of distribution of the G values from molecule to molecule? In the case of an iron sulfur cluster, we know it's due to G value distributions mostly. So the line broadening field to use is called G strain. Strain is the technical jargon in our field for just saying G distribution. And the G strain field gives you the width of the distribution. Okay, let's say we're gonna 0.03 each time on each axis. That's our starting values. Of course, it's anisotropic, so these won't be the final values. We expect them to be different for the different directions. So the largest field feature comes from the lowest G value, which in our case is 1.9. And right now we're starting with a broadening of that 1.9 value by 0.03. So basically the value can vary plus minus 0.03 around 1.9. And the underlying distribution that is assumed is Gaussian. Okay, now we also need to tell the fitting function how much it is allowed to vary these parameters. Now, well, first of all, also which parameters it should vary. That is done by providing a second input structure that has the same form as the spin system structure here. So let's say we want to vary all these parameters. How many do we have? We have 3 for the strain and another 3 for the actual G, center G values. So let's call it sysvary.g. Now, these values are probably still pretty inaccurate. So we might want to vary each of them by, let's 0.05. And this will instruct esfit, which is EasySpin's least squares fitting function, to search within a range of plus minus 0.05 around these start values for the best fit spectrum. We also want to vary the G strain. And for varying the G strain, let's be generous. Let's let it vary a lot. So 0.003. This will mean that we're starting at 0.03, and then we can go plus minus 0.03 from that value. So in the worst case, it gets down to 0, which might be a little bit extreme. So maybe 25 on each of those. Okay, now comes something that is important for esfit, but we haven't talked about before. So this is a little parenthetical exploration here. We need something called function handles. Function handles are a MATLAB feature that allows you to pass a function as an input to a function. It also allows you to make up alias names or new names for functions. For example, a very simple thing is the sign. Okay, let's take the sign of some number. It's a very simple function, but we can define f to be a replacement name for a sign. And so you put this @ symbol in front of the function name, and this will make f basically equivalent to sign. So if I now call f of 0.5, I should get the same as the sign of 0.5. Let me run this with Control Enter and just go look over on the command window what is happening. You see f is defined. It tells it's a function handle pointing to the sign function. If you call f with a 0.5 input, we get 0.4798. And that's exactly the same as if we were calling it with the sign of the same input argument. You can also use these function handles to define new functions in one-line statements. Let's define a function that squares a value. And let's call it g. In order to do that, you again use the @ symbol. And then you specify in parentheses the arguments this function should take, let's say x. And then in one line, you have to specify a statement of what it should do. It should square the function. Okay, so now if you call, for example, g5, actually let's make this a separate section here. g5, it will let's run g this first. Let's look what g is over here in the command window. It's a function handle pointing to this function here, which is a function of x that returns x squared. And now if you call g5, over here we get 25. So these are function handles. They're extremely useful. And in EasySpin, we use them to pass the simulation function that we want to use to the fitting functions. So now for the least squares fitting, we're using esfit. That is the name of the fitting function. And then we have to give it a handle to the simulation function. This is a solid state spectrum. So in EasySpin, you have different functions for different regimes. For solid state, we have pepper. For liquid state, we have garlic. And today we'll learn about chili, which is for the slow motion regime. But this is a solid state spectrum, so we're going to use pepper. So you have to include the at symbol to make it a function handle. This is really important. Don't forget that. So this way, the EasySpin fitting routine knows which function to call to do the simulation. Then we have to provide the data. The data input is loaded in SBC. After that, we have to provide the starting values for the parameters, which is in the spin system, so sys0. And then we have to tell it how much they can be varied, how much plus and minus the function is allowed to go. So sysvary. And of course, we also need to know what the experiment is. So the experiment parameters have to be passed on, and that's kind of the minimum required input. So if you call esfit without requesting any outputs from that function, it will fire up a user interface. And let me run that now. So I'm going to this section here, as to remind you, those who were not familiar ahead of time. You can use a double percentage signs to subdivide a script or a file of MATLAB code into different sections. Wherever you click with your cursor, you see that section highlighted in yellow. And you can run the code within that section by pressing Control Enter on Windows or Command Enter on Mac. Control Enter. And this will bring up this EasySpin fitting interface. On the left, you see a plot of the experimental data. And on the right is all the display and the interactive elements that help you fit the spectrum. Let's first walk through it and see what it is. On top, you get EasySpin tells which function it will be calling. And in this case, it's calling pepper. That's exactly as we wanted. Then comes a list of parameters. These are the fitting parameters. For each parameter, there's one row in the table. And you can see we have the G1, G2, and G3, G-strain 1, G-strain 2, and G-strain 3. There's a checkbox to the left of it. If you uncheck it, this parameter will be kept fixed and not included in, and not varied in the least squares fitting. You can modify your selections by clicking the All button, then you get everything is selected. If you click the None button, everything's unselected. And let's say you've fitted the first 3 G values, now you want to fit the G strains, you just click the Invert button and it will uncheck every checked box and check every unchecked box. And so you could, for example, go back and forth between fitting the G values and the G strain values. So besides the name, you also have the currently best value. That's just a display, a read-only thing here. Then the current value, which is the value of this parameter at this particular iteration of fitting. And then there is an editable field with a lower bound for the search. Let's change it a little bit. And the upper bound for the search. So while the search is going, while you're in this interface, you can change the bounds, the search ranges of each of these parameters interactively. So that is the parameter table. And next comes a section with important settings for the fitting procedure. The first one is the method. And if you click on this, you will see there's a series of different optimization methods implemented. They have varying degrees of efficiency and locality. The top 2 ones, the Nelder-Mead simplex and the Levenberg-Marquardt, are so-called local search algorithms. They find a local minimum it's close to the starting values that I entered. Basically, if you think about our goal is to fit the spectrum, right? So any deviation between experiment and the simulation is undesirable. And what least squares fitting does, it minimizes the sum of squares of the difference between the data and the simulation, right? And ideally, we want to minimize that. And so you can picture this error function or objective function as kind of a landscape, right? And the lower it is, the better. And ideally, you want to find the global minimum of this function, which means you want to find those parameters that make the fit best, right? However, these first 2 algorithms, they only find local minima, right? So they start at a particular parameter point and then just start minimizing. They go downhill until they hit the valley or the bottom of a lake or something. And so if I would do this in Seattle and I would just go down from the hill from here, I would just end up at the bottom of Lake Union, which is not the lowest point on Earth. On the other hand, if you use a Monte Carlo or genetic algorithm or a grid search or a particle swarm algorithm, these 4 algorithms are global search methods. They explore the entire parameter space, not just starting from the start value that we entered, but they generate a lot of different parameter values and explore much more completely the entire surface. So these algorithms are more likely to find the global minimum, which I think is the Dead Sea in Israel/Jordan. And the other methods here, Nelder-Mead and Levenberg-Marquardt, are very local search methods. They're much faster, but there's no guarantee to find a global minimum. So please be aware of that. That's a very important distinction. And the more global a search method, the slower it is, unfortunately. The next important setting is the target function. So typically we just fit the deviation between the experiment and the data, the experiment and the simulation. However, sometimes it's better to integrate the spectra and then do this comparison. And there's also a way to do it with the double integral. You can also take the derivative, or you can even do a Fourier transform, which is advantageous if you have an organic radical spectrum with, let's say, 60 lines, which give you a very, very high structure. Then it's much better to do a Fourier transform before you calculate the error. And that error surface has much fewer local minima. Okay, the third one is the scaling. Your vertical axis of the experimental data correspond to some sort of voltage that you measured or that came out of the spectrometer and was digitized. And Pepper doesn't quite know what scale this voltage is. And it actually, for EPR spectrum, it really doesn't matter, right? As long as you have a good signal to noise. So there is, after simulating a spectrum, there's an extra step that's happening where the spectrum is being rescaled. The simulated spectrum is being stretched or compressed vertically to match the experimental data. And how this is done can be chosen here with the scaling. If you only want to do a scale only, but with a least squares fitting, you just select scale only LSQ. But you also might want to scale and shift it, or scale and also include a linear baseline in a fit, or a quadratic baseline. That's also possible. Or in some cases, especially if you're simulating magnetometry data, your vertical axis actually has some meaning, and then you don't want any post simulation scaling, and you would select no scaling. But for now, let's just stick with scale only. That should be fine because we have a nicely corrected baseline. Finally, there's a start point, center of range, or you could, that's where we're starting, center of the range. So for example, for G2, we would be starting right in the middle between the lower and the upper bound. We could also select to start at a random point within that range, or as we will see, we can choose a specific parameter set that's given down here. Okay, let's start the fit. Let's see what happens. Here on top now it says it's running. And then now here at the bottom you see there's a small error displayed. It shows you the logarithm of the root mean square deviation between the experiment and the simulation. It's logarithmic because it's just easier to display. It's a 10-base logarithm. You can see as you go, the error is decreasing. In red, you always see the current simulation, and in green, you see the best so far. And the best RMSD is also printed here in blue, and some information on the current iteration is shown here. So we're running a Nelder-Mead simplex algorithm. We're fitting the integral of the spectrum. We're only scaling it, and we started at the center of the range. And as you can see, it's walking very slowly, but you can see kind of the trend is that it's slowly decreasing. And the fit is getting better. So you see the logarithm RMSD is below 1.26 already, and it keeps dropping. So Nelder-Mead simplex is a very safe local search algorithm. It walks slowly, but it doesn't get as stuck as often as Levenberg-Marquardt can. So you might realize, oh well, maybe I didn't choose really good starting values. Now what you can do, you can press stop, stop fitting. And now you will see your current best values given here. If you think these are good and you want to use them for anything later on, you would just click here, Save Parameter Set. And if you click that, these parameters that were your current best fit will go down here into a list of parameter sets, which this way you can store different sets and explore different ways of fitting. So let's switch over to Levenberg mark card. We might also want to start, what are you going to do? We just actually, let's fit everything at the same time. That should go better, because we actually previously only allowed the strains to be fit. And so the fitting algorithm wasn't allowed to move peak positions. Actually, let's go back to Nelder meets simplex and start again. And again, we see we start out a little worse, but now we are already better than previously. You can see that all the G values and G strains are being updated continuously. The table is grayed out because while you're running, you can't change any of these values. So we can stop this now. And now we've got a new parameter set, which we can save. And now what we could do, we could switch over to the Levenberg mark-out method, tell the algorithm now to then click here on this, select our parameter set we just saved, and then say the Levenberg mark card should start at this selected parameter set. And click start again. And voila, you see we're there. We got the fit. And it will iterate for a little bit until it's really converged and then terminate by itself. This way of interacting with the fitting routine allows you to do multi-stage fitting. So if you could start out with a global fit, use, for example, a genetic algorithm or Monte Carlo to really explore your parameter interface, let that run for a while if you don't quite have an idea about where the parameters are, and then save the best fit, and then switch your algorithm and kind of hone into the local minimum that you've identified using Levenberg mark-card or Nelder meets simplex. So this is kind of a multi-stage fitting. It's also called a hybrid fitting algorithm. And you can do it basically manually here through the interface. Okay, so now we've got, we can again save this parameter set, which is now the best one. You see, it also stores the RMSD, which stands for root mean square deviation. It's 0.88. That's the closest we got. And the fit here in green looks pretty good, given the noise. Now what we can do, we can export. We can click export, this button here, and it will take the selected parameter set and export it to the to MATLAB, so out of the GUI. If you click export, you will see it prints out that the fit set number 3 is assigned to variable fit3. If you go to the workspace now, you see there is a new variable called fit3, and that variable contains all the information: the RMSD, the fitted spectrum, the experimental spectrum, the residuals, the best fit values, some information of what it actually fit, the spin system, and its ID number, right? And you can then use this. Let's make a new figure here. Actually, let's do it over in a script. You use a figure, and you can say plot fit1.xspec. Let's do a hold on, which means, don't delete the next the plot when I'm plotting something new, and then say plot fit1.simspec or fitspec. And this will plot the two fit, the experimental and the fitted spectrum on top of each other. Let's fit 3. Voila. And this is your manual plotted experimental spectrum plus the fitted spectrum. And now you can use this to make your own final plot and export this figure in a fashion that we talked about yesterday. So this is kind of a very first quick overview of how to fit spectra using esfit interactively. I showed you how to load the data, how to call the esfit function, and then how to interact with this interface, and also how to get the fitted values out back from to MATLAB itself. This is the end of our first session. We've used up all the 30 minutes. So now I invite you to look at the script that you obtained with the zip file, but we'll continue more with least squares fitting in about 10 minutes or so.